I'm going to be talking about packaged CHP systems today. Some of the comments in my presentation relate to combined heat and power in general, all types of systems, but for the most part, I'll be talking about packaged CHP systems. I'll start by talking a little bit about what a packaged CHP system looks like, some of the benefits, some of the suppliers where you can get packaged CHP systems. I'll talk a little bit about the CHP systems that have been installed in the U.S. and the potential for additional installations. And then I'll talk a little bit towards the end of my presentation about how packaged CHP fits into grid modernization efforts, and then also utility participation with CHP, including packaged CHP. When we think of a packaged CHP system, I really think of it as a product in a box. So we've got all of the major components that they're integrated at the factory. It's delivered by a single vendor as a turnkey product. In most packaged CHP systems, I have capacities under about 500 kilowatts, although larger systems are available. I'll talk about some of those, the distribution of systems a little later in my presentation. With packaged CHP systems, if we look at those compared historically to how CHP systems are installed, most CHP systems historically, they're installed as custom engineered systems based on site-specific requirements. With packaged products, however, it's a more streamlined approach. The hardware is integrated at the factory and then delivered as a turnkey product. This is a really simplified illustration of a packaged CHP system. The prime mover, when we're talking about the capacities that for packaged products, you're typically looking at reciprocating engines, maybe a microturbine or a fuel cell. But that prime mover is integrated with the heat recovery hardware and the electric generator and the controls. That's all packaged, tested at the, by the manufacturer, the vendor. It's delivered to the site, relatively simple installation. You need, in most cases, these are natural gas-fired systems, so you got to provide natural gas at the proper pressure for the system. If the heat recovery system is designed for hot water or steam, you got to make the water connection, provide that. And then the product provides electricity and useful thermal energy to the site. With these packaged products, there's a number of benefits, and I'll go into those, some of those benefits or touch on them in a later slide. But from an installation standpoint, the installation for a packaged product is relatively streamlined. You avoid some of the issues that you might encounter with a custom system where you encounter something that wasn't fabricated quite correctly. There's some reworking involved, and you avoid some of those problems or issues with packaged products. This is just an illustration of kind of where packaged systems fit in, kind of into the electric grid in general. Now, combined heat and power systems can provide value throughout the grid, all the way from generation through transmission, distribution, down to the end user. But when we're talking about packaged products, these are typically smaller capacity systems, so we're talking about kind of on this slide at the the right-hand side of the slide. So we're talking about where these packaged systems fit in, and they're going to fit in typically in a behind-the-meter application where they provide benefits to the end user, but also, as I'll talk a little bit later, benefits for utilities as well. So if we think about benefits for combined heat and power and focusing on packaged combined heat and power systems, from a manufacturer or vendor's perspective, packaged systems offer an opportunity to reduce some of the production costs. It's a replicable product that's produced at the factory, not field assembled. There's also the opportunity to simplify some of the sales support. After the product is delivered to the field, it's more of a known entity, a little bit easier to support from the O&M side. And also, I think packaged systems provide some opportunities to open new markets. with package systems, particularly if you have a replicable application, maybe it's a big box store, a grocery store, or maybe a hotel motel with very typical construction characteristics or energy demand characteristics. Those products, packaged products, can fit well into those replicable applications. And there's also some markets where maybe historically have faced maybe some space constraints, and packaged products can oftentimes fit into those markets. If we look at the benefits from the end user's perspective, there's some simplification in terms of being able to specify a product or identify a product that might work for your application. And then also there's a single point of contact for trying to procure the product, get it specified, and get a good match for the end user application. And with a packaged product, from an end user's perspective, they can oftentimes shorten the cycle, the time cycle, from the point when they think, well, yeah, maybe a CHP product might make sense. They can shorten that time from, okay, I'm interested, to the time when they can actually get a CHP system in operation at their site. And of course, lower costs. The economics are a driver for packaged CHP systems. It's a little hard to kind of, wrap your arms around or identify or pull together information on what cost reductions are really achieved. But one reference point, the New York State Energy Research and Development Authority, they've had a program in place for a few years where they pre-certify CHP products, and you can think of these pre-certified products as really packaged CHP systems. And in the NYSERDA program, they report that they've observed about a 25% reduction in overall project costs through these packaged or pre-certified systems. ICF completed some work for the U.S. Environmental Protection Agency earlier this year, and we looked at packaged CHP systems. We talked to some of the U.S. EPA CHP partnership partners. We did some, talk to vendors throughout the U.S. And in our research, we identified 27 different vendors that are offering packaged CHP systems in the U.S. This photo just shows a snapshot of some of those systems. And again, I mentioned it earlier, but most of the systems have capacities under 500 kilowatts, but there are systems larger, up to 1 to 5 megawatts. Now I'm going to show some slides that talk about CHP installations, packaged CHP installations. This slide is perhaps a little hard to read, but I'm looking just at packaged CHP systems, and it's a plot of capacity and installations as a function of size bins. And the size bins start out at under 100 kilowatts, and then the largest size bin is 1 to 5 megawatts. And in the analysis that ICF did, and this is based on some work that we did for the U.S. Department of Energy in 2016, packaged CHP systems going up to 5 megawatts, and that's the largest packaged CHP systems that we identified. There are about we identified 949 installations with a total capacity, aggregate capacity of 215 megawatts. In terms of the number of installations, about a little under half, 461 of those installations were for systems under 100 kilowatts. In terms of capacity, though, the largest capacity, 65 megawatts, fell into the capacity range of 1 to 5 megawatts. This is another chart showing some installation information. I know it's impossible to read along the bottom axis, but what the bottom axis is we divided looked at the installations by market segments. So there's 18 market segments spread across the horizontal axis. 5 of the markets are in industrial, and then we have 13 markets that are collectively comprise commercial, institutional, and multifamily applications. And if you look at sort of dividing those installations amongst those different markets, about 9% of all of those installations, 83 of the installations, were what we considered industrial markets. And then there's about 91, little over 90%. 90% of the installations are in the commercial, institutional, multifamily type markets. This next slide is real similar to the previous slide. So we've got the 18 markets on the horizontal axis, but this is a plot showing the capacity of how the capacity is spread across those 18 markets. The industrial applications are typically larger capacity systems, and so what we see here is the industrial markets. Those 5 industrial markets account for about 18% of the capacity. And then the commercial, institutional, multifamily, about 82% of the capacity. Now, the previous 3 slides that I showed, that's looking at, okay, what kind of packaged CHP systems are installed in the U.S. currently. This chart starts to take a look at the potential for additional CHP installations. And in this chart, I focused the analysis just on 500 systems under 500 kilowatts. And based on work that ICF did for the U.S. Department of Energy in 2016, we identified a technical potential for under 500 kilowatts of just over 21,000 megawatts, so 21 gigawatts, so a big number of remaining technical potential. It's important to recognize that number, over 21 gigawatts of potential, that's technical potential. That does not take into account economic factors, which of course is going to shrink or narrow that potential. But from just a technical or perspective of matching on-site technical requirements, we had over 21 gigawatts of remaining potential. And if you compare that to what's currently installed in under 500 kilowatts, there's only 300 megawatts of all types of CHP and about a little over 100 megawatts of packaged CHP. So the takeaway message is there's a big technical opportunity, but again, that needs to be, taken in context. It's not the economic potential. But there's takeaway message, there's big potential for CHP systems. So now I'm going to talk a little bit about kind of how CHP fits into some of the grid modernization efforts. And certainly there's a lot of attention being placed on modernizing electric grids in New York with their Reforming the Energy Vision Process, REV, California, a number of western states, and other states throughout the U.S. are undertaking efforts to modernize electric grids. And along the left-hand side of this chart, there's 7 different grid modernization goals. And these goals, and so like grid reliability, customer resilience, energy efficiency, the DER integration, the distribution energy resource integration, some locational value, some cost or affordability, and emissions reduction. And if you look at those goals, CHP systems in general, all different types of CHP fit into or can address those goals, and packaged CHP systems as well can fit into achieving all of those goals. So, when we think about how packaged CHP systems can enable grid modernization, we see it as having fitting well with those initiatives. This slide looks, I've just picked off a handful of just 3 different opportunities thinking about how utilities can participate or gain value out of combined heat and power. And I've tried to focus these on packaged systems. It's not entirely packaged, but there's 3 opportunities or three angles for utility participation. The first one on this chart is using combined heat and power in energy efficiency programs. And one example that I've included here is with Baltimore Gas and Electric. ICF implements an energy efficiency program for Baltimore Gas and Electric. And what's really interesting is that Baltimore Gas and Electric does include CHP as a energy conservation measure, and looking, what some of the latest projections show is that Baltimore Gas and Electric is projecting or forecasting that they're going to get about 20% of their energy efficiency goal from combined heat and power. Now, most of those, not all of them, not all of that goal is met by packaged CHP systems, but a big part of the goal is achieved through what we would consider to be packaged CHP systems. The second one is using CHP to either, as a distribution system resource, so that could be deferring transmission or distribution system upgrade. And one of the examples that I've listed here is with Consolidated Edison in New York. They were looking at, or had a serious grid constraint. They were looking at non-wires alternatives, and as part of the non-wires alternatives, they included encouraging combined heat and power. And it's interesting to note that in this grid constraint area, which they refer to as the Brooklyn Queens Demand Management area or program, they captured about a little over 3 megawatts of CHP to help them achieve that non-wires alternative goal. The last item on this slide is talking about utility-owned CHP. And this is not a packaged CHP system. It's a custom engineered system. It's an example where Duke partnered with Clemson University to install a 16 megawatt system. But I list it here because I do think there are opportunities for utilities to aggregate smaller packaged CHP systems and provide and participate on an ownership basis and to meet their objectives as well as end user objectives. So in summary, just a few takeaway messages. Packaged CHP systems provide value provide benefits throughout the value chain, starting with manufacturers, vendors, end users, and utilities. I think that there are opportunities for all of those players to participate. Packaged CHP is a great fit for replicable applications. Big box stores. Grocery stores, could be Whole Foods or hotel chains. And then also, I mentioned it earlier, but opening up some new markets. And then just a final comment, the U.S. Department of Energy is undertaking efforts to help encourage packaged CHP, and one of their efforts is the development of a e-catalog. It hasn't come out yet, but it is some work underway with DOE. I did leave some handouts of the presentation at the back, and I think I left also a handout on some grid modernization, but thanks a lot.
Thanks, Rick. All right, so we'll save questions again for the end. Again, welcome for those of you that came in the middle of Rick's talk. Welcome this morning. Glad to have you. Again, this is being recorded, and the papers will be uploaded to the PowerGen website by the end of this week, if not first part of next week, so you can access any presentation at the show that you like. Okay, so with that, our next speakers are Don't Freeze in the Dark, how the University of Alaska Fairbanks is building what may be the last new U.S. coal plant. Charles Chilcoot Ward is Director of Utilities at the University of Alaska Fairbanks, and which provides heat and power to over 3 million square feet of buildings on the largest UA campus. He has over 30 years of construction and engineering experience in commercial, power generation, and mining projects. He holds a BS in mechanical engineering from the University of Alaska Fairbanks and is a licensed PE. John Solon will be the second speaker. There are 3, I'll let you introduce yourself when you come up here, since I don't have it. John Stone's a mechanical engineer with 18 years of experience in power generation, where his experience includes a wide variety of power plants, from retrofits of large coal plants to new simple cycle aeroderivative installations. A primary focus of his work has been with the combined heat and power facilities. He's been actively involved with this project for over 5 years and has experience as a facility mechanical engineer at the CHP plant at the University of North Carolina at Chapel Hill. So with that, get you guys set up.
Thank you, Peter. It's interesting that we've given a presentation on trying to get funding for this project for a while, and we've used this picture numerous times, and the existing power plant is just off frame in the photo, so there might be a message there and might not. Anyways, about a little bit about the University of Alaska Fairbanks. We were founded about 100 years ago. We are located in Fairbanks, Alaska, which is the middle of the state. We have about 10,000 students, which doesn't make us a huge university, but we're very big in research. Research is very important to the university, both from the standpoint of reputation and also for dollars coming into the university. We do have a very wide temperature extreme in our locale. 100-degree temperatures is not uncommon, and also 60 below. So that makes a very large challenge to provide the utilities. But basically, my job is to provide the heat and lights for the 3 million square feet for that campus. Also, if you look at the one photo in the shot there, the university also owns a suborbital rocket range. So again, not quite a power thing, but still pretty cool. Our issues. Our current CHP plant, which is the second CHP plant on the campus, this is a coal-fired facility that is 50 years old, and unfortunately it's too small. And since it's too small, we've been running at 105 to 110% of its rated capacity for a lot of years, and we wore it out. So we need to come up with something to do differently. We've looked at renewables. They're not realistic in our climate. We don't really have the right solar. We don't have wind. We don't have hydro. We don't have geothermal. We're kind of stuck. And oh, by the way, we really don't have natural gas. We have trucked LNG, or as I refer to it as unnatural gas. They buy gas 350 miles away, liquefy it, haul it up, gasify it, and sell it to us at a nice discounted price of $19 per MCF, which is subtly more than most people pay. In addition, we have a lot of coal. Alaska has half the U.S. coal reserves. Nobody knows that. We have one working mine in the state. So anyways, what is our objectives? We need to make sure that we meet the heat and light demands for the next 30 years. And that's kind of a tough thing to do, is to actually predict that, but we did our best efforts to do that. We need to reduce emissions. That's a big thing. We are a university. We're supposed to be leading the world in climate change. Again, a huge thing. We need to lower operating costs. The state monies are getting tighter. And because of that, there's a lot of pressure to try and do more with less. Increased reliability, or resiliency is another way to think of it. Since we do have a lot of money tied up in research, if we start missing satellite download passes, we'll stop getting government grants to do that, and then the revenue stream to the university dwindles. So this is a huge thing to make sure that all of our functions stay running all the time. And we, again, the power plant wasn't that first shot, but it's a small area to work in, so it's a fairly tight site. And to really compound the issue, we happen to be in a serious PM 2.5 non-attainment area, which means we couldn't even get a wet tower permitted because they make too much particulate. So, and to further that, I have a boss who isn't just a environmental person by actions. or by statement, he does actually believes in trying to do things for the environment. So I'd like to bring up to the podium Mr. John Solon, who will talk about the options we looked at and some of the solutions.
Thanks, Chokut. So the university knew they needed to do something, but they weren't sure what. And in addition, they were kind of concerned about the community's reaction to replacing the plant. Fairbanks is a very tight-knit community. Everybody knows everybody else. In fact, the state of Alaska is a lot like that. And so to kind of get ahead of the curve of well, why didn't you, or did you consider questions, not only from the people in the local community, but also the politicians in Juneau, they hired a company called JLHN to evaluate a number of different options. It's a screening study. And so this was taken under about 10 years ago. And the options they looked at were just about everything they can think of. That goes from the standard, do we just rehab the boilers and keep going like we are, to replacing the boilers with CFBs, replacing the boilers with gas turbines at HRSGs. Do they go to gasifiers, either coal gasification or MSW? They even looked at just throwing the boilers out entirely and converting the campus to all electric. On top of that, they also looked at a small modular nuclear reactor just to say that they looked at it. So the results of the study, it's pretty clear. This is just a summary of a total cost evaluation. It includes capital costs, overhead operational costs, and energy costs. As you can see, the all-electric solution wasn't particularly desirable. It turns out that option number 3, which is a circulating fluidized bed boiler and producing all the heat and electricity needs of the campus, was the most cost-effective over the life of the plant. So at this point, this is where the university decided to go ahead with the project. They brought Stanley Consultants on. The first thing we did was a feasibility study. We mainly focused on coal technology, that not only CFBs but also BFBs and stokers to start with. At the same time, we also did we projected load growth over the life of the plant, and so when we started looking at the different technologies and with terms of load growth and in terms of predicted emissions, it quickly became clear that the BFB and the stoker technology was not going to be an acceptable solution, because we just could not install that equipment and get the capacity we needed to stay underneath our emissions cap based on the netting analysis. So we started to proceed down the path of feasibility study for a CFB solution. We did some initial cost estimates. The cost estimates were fairly in line with what we would have expected for the project team, but it did raise some additional questions outside of the project team and some additional concerns about the total cost of the project. So we took a step back, and in order to once again get ahead of the "why don't you" blank question, we took a look at 2 other options again. We revisited buying all electric power, and we also revisited building a natural gas plant. Now, I don't think it's, as you see from the previous graph, I don't think it's very difficult to understand that the all-electric option didn't go anywhere once again. We did take a really close look at building a natural gas plant. The main problem we had with that solution was that there was no reliable source of gas. So included in that project was an LNG receiving, storage, and vaporization facility dedicated to the university. Even including that, and including the cost of the turbines and the HRSGs and the backup boilers and all the other ancillary stuff you would need for a CH plant with a gas turbine, it turns out the capital cost was less than the CFB option, but when you figured in the cost of fuel over the next 30 years, it quickly became apparent that it was going to cost the university 2 to 3 times more to install a gas plant than to install a coal plant. So the results of that study was sufficient to convince all the stakeholders that the CFB project was the way to go. After several rounds of value engineering and optimization, we wound up with what you see on the screen here. We have a single circulating fluidized bed boiler capable of producing 240,000 pounds an hour. It's connected to a 17 megawatt condensing single auto extraction steam turbine with an additional uncontrolled extraction. That turbine's connected to a gearbox and a 12470 generator. The condensing is done by a 3-cell air-cooled condenser that is specifically designed for the environmental conditions in Fairbanks. Specifically, it'll run at low loads at minus 66 degrees F. It has upper and lower louvers, variable speed fans with reversing drives. The emissions control is very simple, given the nature of the CFB. It's just a baghouse with a DSI system. The DSI system is purely there just in case the boiler had problems making its PM 2.5 emissions. If that's the case, they'll turn it on and get a little acid gas trim, and hopefully that'll get us under the limit. B&W included that as a precautionary measure. With any luck, we'll never use it. Of course, given the weather, the coal handling and unloading system is enclosed. And hitting back to Chilkoot's reliability and resiliency concerns, we included a common steam header back to the existing Atkinson plant where they have 200,000 pound an hour package boilers in the existing steam turbines. So they can run either plant. They can run the boilers in the old plant and run the steam turbine in the new plant. They can reverse it. It's really flexible. And there's a fairly high level of redundancy that was built into this plant. So that brings us to the environmental benefits, which is the main way we sold this to not only the legislature but also to the public. In Fairbanks, like everywhere else, everybody is concerned about emissions and pollution. And so the university spent a lot of time with local groups making sure that they understood that this new plant, even though it was burning coal, we're going to see significant reductions in emissions on when you're comparing 1,000 pounds an hour to 1,000 pounds an hour. This chart represents that analysis. What this chart shows is a day one switchover. If you were to produce 100,000 pounds an hour from the existing plant one day and then switch over and produce 100,000 pounds an hour from the new plant the next day, these are the emission reductions that you would see. The main problem area with this one was, of course, PM 2.5. We were very, very close to our limit. In order to stay under the netting analysis for this plant, we needed an emissions rate for PM 2.5 of 0.012 pounds per million BTU. This represents a new layer, a lowest achievable emissions rate for any CFB in the country. We're sorry. But that's what we had to do to get this plant constructed. Again, we traded emissions. The netting analysis had traded emissions from 2 existing stokers that are being decommissioned at the end of the project. The beauty of the CFB has allowed us to stay under the emissions cap but increase our steam production by 240%. With that, I'd like to turn it over to Mike Ruckhouse. He's going to give us an update on where the project is today and talk about the vendors that are partners with us in getting this project up and running. Mike?
Thank you, John. So I'm Mike Ruckhouse. I'm the project manager, and I work for the University of Alaska. I've been there for 20 years. One important thing to add is everything looks at ROB as emissions, as technology, fuels for carbon emissions. And a really important selling point for us on this project was taking advantage of the efficiency of newer technology than the 1890s vintage stokers, I mean, from a technology point of view. And, just getting 20% lower carbon emissions just from using new technology, same fuels, it was an important point, and we brought that forth as we tried to get the public behind the project. Again, now it's all fine in the planning stage, but now it's time to get the project built. And the university had a twofold prong to that. We did major equipment procurement by the university, so initially. And then the other major decision we had to do was decide the project delivery method. And it's very common in this day and age, everybody goes EPC. We looked at EPC really closely, but in the end, we decided that a construction manager at risk or CMGC would fit the project better. The university has experience in managing large projects and some industrial projects. It was a little bit of a stretch for us, but we went on to that. The contractor selection, although there are price elements, there's a lot of, I call it good guy points, qualification-based selection. And we ended up selecting Haskell Davis JV, which is Haskell Corp out of Bellingham, joint venture with Davis Constructors out of Anchorage. I think now that the project is 80% complete, sort of the risk to go to something where the owner is integrated in the management of the project and the vendors and the engineering, we received some skepticism from people outside the project, but at 80% complete right now, we're on budget and on schedule. I'd say it's been a good partnership. We had some huge challenges, and through the teamwork that we brought the right people to the table. We had one struggle to get rid of a $50 million scoping gap, and we did that in a 4-month period, rewrote all the major contracts and got going again, which I think is lightning speed in the power and especially public contracting world. In construction here, probably one of our biggest challenges was wintertime construction. We had temperatures and cut off on site of 30 below, but we constructed all last winter, made decent progress. We met all our production goals throughout the winter. I think we only lost 5 days of total shutdown, and we had partial shutdowns on probably about 14 days throughout a whole winter. Our workforce is very used to working in winter conditions, and it really proved to be a good decision to work through the winter instead of winter shutdown. As I said, we're still staying on schedule and on budget based on our assumptions. So the major vendors that we selected, obviously the boilers in the center of the universe in a coal plant, and B&W has been our boiler vendor. We're very happy with the design, the emission characteristics that they brought to it, and we're going through. We've passed hydro, and we're looking forward to first fire next June. We have some balance of plant things to catch up. The turbine generator is Shin Nippon in Brush. It's interesting to note that since the generator was made in Europe and the turbines in Japan, they never saw each other till the site, which we were a little nervous about, but that's been working fine. And then also on the control side, the Emerson Ovation is what we selected for controls. And you can see the rest of the major vendors there. I think the management method we try has really fostered cooperation. Obviously, every time in a complicated project, there's rubs and issues to be solved, but we're really pretty fortunate to have a group that's dedicated to make the project successful. I know that questions are later, but I just want to share something, a favorite pastime of our student body here when it gets cold. Sometimes we have traffic jams down by the sign, so everyone would get their picture taken there. So, thank you.
Wow, that's interesting. Thank you, guys. Nice job. That's pretty interesting. All right. Our next speaker is Mr. Tom Drake, who's the Regional Sales Gas Manager for North America for MTU On-Site Energy Corp. Tom works for MTU On-Site Energy in the Gas Power Systems Group as Regional Sales Manager. He's 17 years of experience within the power generation and manufacturing industries. In his role as Regional Sales Manager, Tom supports MTU's distribution network, working with engineers, end users, and project developers to properly apply MTU's reciprocating engine technology in gas-to-power applications. His focus is on behind-the-meter power generation both combined heat and power and demand management, along with waste energy projects producing biogas for power generation. Prior to MTU On-Site Energy, Tom worked for Lewis Perry and Associates, a CDM Smith company, as a customer service manager, developing energy projects for their design build group.
Thank you.
Whoops, wrong one. Here we go.
There we go.
Perfect.
Thank you very much. The mouse work to do the slides? All right, I have to reach down. All right, thank you very much for attending, and this is gonna be kind of a motorcycle ride through museum. You know, when I was told I only had 20 minutes to speak, I'm gonna try and jam as much information as I can into our 20 minutes here as possible. So the agenda that we're really gonna look at, a real brief overview in combined heat and power. If you're in this room, you should probably know what combined heat and power is. If you need an education, come talk to me afterwards. We'd love to talk to you. We're gonna review the economics of CHP. I should have worked with Rick a little bit better. We're going to talk about the market potential in the United States, locations and applications, and then we're going to focus on a specific application at a beverage facility. Combined heat and power, the simultaneous creation of electricity and thermal energy, either in the form of steam or hot water, gas. You can use anything, any primary fuel to turn the engine, then create electricity and hot water that you want to deliver to the customer. An analysis of combined heat and power systems, usually you start with a spark spread, which is the cost of the fuel versus the cost of purchasing that electricity. On the United States CHP partnership website, they have a really good spark spread analysis program. If you have a facility, if you're interested in an initial review of combined heat and power, I would always recommend going to that site. You can plug your facility's information into that, and it'll really give you a really good brief analysis. One of the things that we always look at, this is everybody has seen different versions of this slide. Grid-created electricity delivered to you at your homes or at this facility is roughly about 33% efficient, with losses in heat during the creation and transmission. A well-designed packaged cogeneration facility can be upwards of 91% of total efficiency. So 91 units of 100 units used to create that electricity can be used on site. In an engine, MTU, we focus on reciprocating engines. We really look at the creation of electricity through the use of natural gas in our applications. So 100 units of natural gas going in. The electrical efficiency can be anywhere between 45 to 48% total electrical efficiency. We have waste heat going off the stack in the exhaust, and then in the engine water itself, we can collect another 25%. So half of the energy can be used in electricity, and then almost half can be collected from the different heat sources of the engine. Now, this is really my favorite slide when we talk about projects for combined heat and power. If you look at the life cycle cost of a well-designed cogeneration plant, 70% of the life cycle costs are in the fuel. So when you ask yourself the question, what am I replacing at my facility? Am I replacing the cost of electricity, or if I'm replacing the cost of the thermals that I am buying from the utility? So this will tell you what type of technology that you want to use. Size obviously will be a very large indicator of that as well. But the fuel that you're going to purchase, what are you going to offset with that fuel that purchase? If it's electricity, in a lot of cases, a reciprocating engine is going to be a better choice because of a little better total electrical efficiency. And you can see a total project cost, the capital cost, is very small, only 5% of the total project. So you really don't want to look at if technology XYZ is maybe $100 more expensive than technology ABC. You really want to look at the life cycle cost, the operational cost, really, which are going to add up to much more of what you're going to look at as you own that piece of equipment for the life of it. When you look at combined heat and power, especially here in the United States, there are lots of excellent resources. The United States Technical Assistant Partnerships has locations and offices located throughout the country. On the presentation, as it's loaded into the website, all of these links are active. So you download it, you can email, if you have an office in Chicago and you want to put a CHP system in, you can email the Midwest Technical Application Center. They offer free assistance, free analysis, and are really there to help put combined heat and power systems into use. And once again, we're going to talk about one of the applications. We're going to talk about Baltimore Gas and Electric here in a second. But there are utility programs all over the country that are offering promotions and incentives for combined heat and power. California has a self-generation incentive, and that's based mostly on total efficiency of the project. And you have to be over 60% to qualify for the different incentives. Desire, DSIRE, is a website that tracks every renewable energy incentive across the United States. Once again, this is an active link on the website, on the presentation. You can type your state in, you can type the different kinds of incentives that you're looking for, and it will tell you what's available. And then also over here, you have some of the utilities that already have CHP programs in this place: Baltimore Gas and Electric, Dayton Light and Power, AEP, Commonwealth Edison. So there are incentives all over the country. The specific one we're going to look at closely, kind of as an example, is Baltimore Gas and Electric. And this is I use this one because it's kind of representative of some of the ones that are in place around the country. So there's 3 phases that they incentivize as part of their utility program. The design incentive, which is good for up to $75 a kW. The installation incentive, so for projects under 250 kW, which would be more of a packaged unit, it's good for $275 a kW, and above, we're at $175 a kW. And then this is the important one. Once you install the CHP unit, it actually has to run. You get 7 cents a kilowatt hour for 18 months. And the project is capped, the project incentives are capped at $1.25 million for production and $1.25 million for design and incentives. So, we always have to have a good example. So a 1 megawatt generator installed at a hospital. So you get $75,000 for a design incentive. I think most EPC contractors would take that as a good down payment on a study. Installation incentive, $175,000. And 18 months of runtime, you're going to get $787,000. Good for just over $1 million of incentives for a 1 megawatt CHP project. It's free money, just doing a well-designed, well-put-together job. Market potential. As we all have seen this slide as well, gas and electricity prices are going to continue to rise. We look at, as a group, we look at if you're paying over 7 cents a kilowatt for electricity and a reasonable amount for natural gas, there is a technical potential for a financial payback for a CHP system. So if you look at MISO, PJM, CalISO, you're all going to be, by 2020, 2022, you're all going to be above, you're going to be at 7 cents or above on wholesale market prices for electricity, with natural gas being right around the $6 an MMBTU. So good technical potential and good financial potential for combined heat and power installations. I always like this map because it's going to go very well with the next map that I show. But in the areas of the country, the darker the colors, the higher the cost of electricity, and the better the technical potential for combined heat and power. So that map goes very well with this map. If I was better at PowerPoint, I could overlay them. But you can see darker areas where higher electricity costs are, and better technical potential for CHP. This was taken from the Department of Energy's technical potential for CHP study that was put out in 2016. Once again, same kind of map. Now we're looking at the different types of utilities and the different types of industries that can be supported by cogeneration at these facilities. Refining, you're going to look in Texas, oil refineries. Most of these kind of applications are going to be industrial turbines. Lots of steam, lots of thermal production, and the offset of electricity is secondary. Now, Once again, this is a slide and some data taken from the technical potential study. So what we look at as recips, we really look at 5 megawatts and below for reciprocating engine combined heat and power applications. There is 26,189 megawatts of technical potential across the industrial sector at 47,000 different locations. So when we look at this, once again, we look at number of sites and megawatts of capacity. So in the 1 to 5 megawatt sites, which is really what we're looking for industrial applications with good sized reciprocating engines, there's lots of sites, lots of technical potential. And in this one, once again, you see lots of technical potential, a lot of sites, not many megawatts. So you're going to see smaller package systems, micro turbines, and maybe some fuel cells and some smaller package CHP. And the nice thing when we look at industrial applications is they're usually high coincidental thermal and electric loads. Once again, another slide from the technical potential study, and we're going to focus specifically today on the case study on food processing. You look at the install base right now is right around 5 megawatts, and there's probably another 5.5 to 7 of technical potential in the United States. And once again, we're looking at specific technical potential for food. Once again, we're looking at the 1 to 5 megawatts and 500 to 1 megawatt size ranges where we see most of our economically potential industrial CHP and food and beverage industries. All right, now we're going to take a quick review of the case study. This is a beverage facility in the Midwest. It's a bottling plant that operates 6 days a week with 3 shifts of operation. We looked at two options. We've been looking at 2 options. One was a 1 megawatt natural gas peaker to handle their peak loads, and the other one was a 3.5 megawatt reciprocating engine with steam heat recovery project. This is kind of an eye chart. It gives you the facility usage for gas and electricity for a fiscal year. We're going to clean it up here as we go, but this is the natural gas usage. One of the reasons we ended up looking at a reciprocating engine instead of a turbine, obviously because we're reciprocating engine manufacturers, but we also want to make sure that we install the correct equipment for the customer, and because of the cyclical nature of the batching at the facility, the engines and the ability to turn the engines down to partial load and still create electricity made the most sense for this particular application. And also we were able to do a base load of steam and use the existing on-site boilers to match the peaks. So we focused on the electricity cost. The average monthly usage was about 2.5 million kilowatt hours. That included the fixed usage and the demand costs. So they were right around 30 million kilowatt hours annually. Their monthly costs were about $180,000 with about $2.1 million electric bill. So if we graphed their usage, like most Midwest, you're going to get a little bit higher electricity usage in the spring and the summer. You can see over here, we're just under 6 megawatts in the peak in late August, early September. So this would have been the application if we would have looked at a demand response generator. So about 1 megawatt would have used and made this kind of peak disappear, would have reduced their energy set aside annually, but it wasn't really going to give them enough benefit, so we went on directly to the cogeneration application. So a 3.5 megawatt system would cruise along 24/7, produce all the electricity needed on a daily, and weekly and monthly basis, and allow the utility to handle the peaks. So the study at the site, we decided with a 3.5 megawatt system designed for continuous electrical and steam production. And their annual electricity rate in this part of the state, they were at 10 cents a kilowatt hour, and the gas was about $4 an MMBTU. So we looked at a payback of about 4 to 6 years. This is a graph monthly basis, so really we're hitting the electricity right on, both in kilowatt hours and demand. And and engines are not great at steam. I'll always admit that right off the bat. But we were able to the generators were able to do the base load steam, and the existing boilers were able to pick up the peaks. So one of the things that we look at is, you know, especially at the early stages of a project, is not only how much does the equipment cost, but how's it going to cost to install it. So kind of a rule of thumb for reciprocating engines is $1,000 to $1,400 a kW installed. So a 3.5 megawatt project should be right under $5 million for the total project cost. We rounded up to about 5.1 with net savings annually of about $78,000 a month, and the payback was just over 4.5, close to 5 years. So this is, you know, the problem becomes, this is a benefit slide, but you know, some of the benefits is what we talked about when Rick was there. You can lower your operating costs, your facility uptime is going to be greater, you can do some grid support with the units, and then you also can control the quality of your production process. You know, if they lost power or steam during a batch, they'd have to throw the whole batch away. So with some on-site control, they were going to be able to less production losses. But the barriers, most industrial companies are really shooting for that as quick payback as possible. You know, everybody says 2 years, and they try to hit that because they don't really understand that a cogeneration unit is going to be able to provide them 20 years of life cycle costs and savings, but they have to spend that 2 years of capital right away. So that really is a big barrier when you talk to an industrial customer about a potential energy plant at the backside of their facility. You're going to disrupt the traditional utility model. So the utility is not going to be maybe necessarily happy that you're there. Do you have enough physical property to put 3 engines or a turbine at the back of your facility? And it's really not something that you're used to. This is not something that your employees know. They don't know about a reciprocating engine. They don't know what the different things that are going to go into it, so they're going to have to modify their traditional business model. So that's kind of a motorcycle ride through it. Thank you for your attention, and we'll be more than happy to answer questions at the end. Did I hit it right on? Thank you very much.
Thanks, Tom. Pretty interesting. All right, thanks again, Tom. That was, okay. Here we go. All right, great. Our next speaker is Dr. Joseph Pettick, who's an officer with VTU Energy GmbH out of Austria. He holds a master's and PhD in chemical engineering from the Graz University of Technology in Austria. He has more than 20 years of experience in thermal energy conversion and power generation technology, in particular in thermodynamic simulation of power plants. With that, Dr. Pettick.
Thank you very much, Peter. Good morning, ladies and gentlemen. I'm very happy to be here at this conference. I'm, I think, ranked very high in the contest for the longest title of a presentation. I used it also for the abstract submission. Everything is in there, so we have a new approach for predicting the performance of cogeneration and tri-generation plants. I split the title in 2 parts, and actually this is the more important one, because we are trying to look more with more detail at the engine characteristics. More about that later when I talk about the details of the engine modeling and the CHP application examples. My co-authors are Peter Bechtel of VTU Energy, Milt Venitos of Wired Enterprises here in the USA, and Mr. Marco Dieleman of M&M Power Solution in Thailand. And in my speech, I will want to go through a quick introduction of my company and of the topic, but then I'll present the model that we developed for the gas engine, diesel engine, or dual fuel engine performance characteristics. And I'll give 2 examples, one tri-generation and one cogeneration plant, both with quite interesting efficiencies, but this is bought at a high level of complexity, and this is why we think you need a good modeling tool to investigate such options. The name VTU is an abbreviation for 3 German words. In English, Process, Technology, and Environment. We are part of a VTU holding group of 450 engineers, most of them based in Europe. And VTU Energy is a company that concentrates on consultancy and software systems for the power industry. And our applications lie in all types of thermal power generation. So we cover coal, gas turbine-based power plants, solar, and cogeneration facilities. And the key tool to our work is a simulation software. It's called Epsilon Professional. It comes from Germany, and VTU is a co-developer of this code. And this software allows us to model the entire power generation system, the heat exchangers, the novel technologies. You will see it in the examples. We can also include absorption chillers, compression, heat pumps. And most of all, it's not nameplate performance only. It's not only the baseload performance, but it is full off-design capability of that model, so you can really simulate the plant under the entire range of operating conditions. And in times of more flexible power generation, more fluctuations in the market, the renewables, they bring up a lot of disturbance, and therefore the highly flexible gas-fired plants are required to fill the gap, to ensure that the electricity supply remains reliable. The units become larger when we talk about gas engines. Just because of that reason, we have also in VTU one project completed in Oman with a 110 megawatt gas engine plant with Wärtsilä units. That was for a different product of ours, a settlement system, but nevertheless, it is becoming also a utility scale technology. And because of the high efficiencies and also the startup capabilities of the units, they become more popular and they become larger. And the waste heat from these units, they are, of course, as we already heard from other speakers, this heat is, of course, valuable and can be used in CHP applications. But the core part that is missing, and that's what we added to our software, is that in order to do a full off-design analysis of a CHP plant using a gas engine or diesel engine or a dual fuel engine, is that you have to describe the unit also in terms of mass flows, temperatures that are connected to the external systems, your heat exchangers, your cooling systems, the other equipment in the overall process. It needs to be in line with the current performance of the plant, with the current operating point. So the engine model has to include all of the operating characteristics of the engine. On this slide, you see how it looks like in the Epsilon software. This unit here is the gas engine component. It's connected to an airstream here, inlet air, suction air. It may be preheated and conditioned. There is the exhaust gas stream. Fuel may be gas or liquid fuel. And then, of course, most important for the CHP applications, there's up to 3 connections where you can integrate the cooling cycles of the engine with a system to generate useful heat or to drive chillers and other equipment. All of that is fully calculated in the heat balance software, mass and energy balances. So every stream, as a result of the calculation, is with its full conditions, and you can describe with all of its properties. And you can, of course, generate a balance of the heat that goes into the engine and the heat produced, and you reach the overall fuel efficiency numbers. So you have about as we heard from the speakers before, in the range with the large units, 45 to 48% electrical efficiency, but you can come to the exceeding 90% of fuel efficiency when you integrate the cooling cycle heat that is rejected. Now, how do we implement that in our software? One is the performance data, electrical performance. That is through, sorry, you cannot read that at that size, but we provide the performance information, the rating data, so a rating point, and rating conditions. And in order to account for limitations that may exist for the unit, we also include a section that will warn the user when he is exceeding vendor limits for, let's say, heating value range, lower heating value, maximum temperatures, maximum altitude for operation. And this performance information is then for part load and off-design operation. It is mapped with 1D or 2D correction curves for the parameters suction, inlet air, and engine part load. And as a third option, if you really want to go to the very detail, and if you have good data on the performance of the engine, you could also include another 2D correction curve to account for inlet cooling fluid inlet temperatures, how they shift the heats between high temperature, low temperature, and oil cooling cycles. But the core part to our system, and I think this is the differentiator, there is also other software on the market already, but the core differentiator in our system is that we include a heat rejection scheme, which describes the control scheme for temperature and flows in the engine as a function of load and of engine configurations. We have built in cooperation with vendors. We talked about our efforts, and we developed a generic model that hopefully fits all of the vendors, at least those that we talk to, it fits well. So you can define internal sources for the heat. This is the jacket cooling, oil cooling, turbocharger, intercoolers, generator cooler. That is generic, so you can define those heat sources inside of the engine. And then the engine manufacturer may route his cooling streams through those heat sources. So this is a configuration, where in this example, there is an oil cooler that takes from the oil cooler here. So there's one here and one here with fixed flow. And then there is the high temperature water go through two coolers, turbocharger intercoolers, and it is controlled by a temperature setting inside of the engine. In the scheme, you can read that from my paper with more detail. In the scheme, that is transferred then to a table that we fill up with vendor information for the individual engine, where we include the amount of kilowatts from the individual sources at rated conditions, and the correction curves will then transfer that to off-design operation, and where the control scheme of the individual cooling cycle is defined. There is options for flows. It may be a constant flow. It may be a flow that is controlled to reach a certain temperature, and these temperatures are defined here. Unfortunately, too small to read. Now I come to the first example of such an integrated system. So this is an epsilon model where we model a tri-generation plant based on an MAN diesel and turbo 20V 3544G engine. It's about 10 megawatt rated performance. Has an electrical efficiency of more than 45%. And in this tri-generation cycle, at base conditions, we come to a value of 87.4% overall fuel efficiency. This is achieved by, if I start here, so this is the return temperature, 140 F. This flow goes through an LT, an oil, an LT, cool low temperature heat exchanger connected to the LT cycle, an oil cycle heat exchanger here. Then it's going through one exhaust economizer here, and through the high temperature heat exchanger, and another high temperature exhaust heat exchanger to produce 248 F hot water. In addition, there is a lot of pipings shown here that are required to fulfill the requirements on the control side here, because the engine is, of course, very much affected by the cooling fluid inlet temperatures, and they have to be controlled in a certain range. So in part load operation, these need to be adjusted according to the change in heat rejected on those individual cooling cycles. The hot water can go two ways. One way here is then through an absorption chiller that produces chilled water in the range 43 to 56 F here. And the hot water coming back from this chiller is also used for a heating application and a high temperature heat application here. The system, this is another view, includes in the model, of course, different controllers that match all the requirements that control individual flows, bypass flows, cooling tower bypass flows, here a temperature control flow, in order to meet the requirements of the individual equipment at different load levels. And with this model, once it's designed, you can run the entire operating range of the engine. And we believe at VTU that this is important when it comes to larger engines, because these do not run, as my predecessor spoke, as a base load engine where they run at full load all the time. The larger the engines, the more likely it is that they will have to part load. And this you can investigate with the software. And we also include on the absorption chiller a detailed model, a curve-driven based model based on vendor specifications. The result for a temperature swing in the plant is quite astonishing on the first view, because here the ambient temperature of the plant is rising. And if you look at the fuel efficiency of the plant, it's rising too. It's very unexpected. But the reason for that is simple. At this temperature around 80 F, the cooling tower performance starts to decrease. Yeah? You cannot produce, your cooling tower return temperature is high enough to become so high that the absorption chiller starts to reduce capacity. So the chiller capacity goes down. The heat from the flow, from the exit from the chiller also goes down, and the heat that is in the high temperature cycle goes up, and this is then producing a higher usage of the heat in total. But the chiller, of course, will have a better price. So in fact, higher temperature will reduce the income of the plant. If you look at the load swing of the engine in the next slide, it shows a very strange behavior. The red curve here is the overall fuel efficiency, and you see that there is up from 100 to about 72%. There's a decline in fuel efficiency. This is typical, of course, because the engine efficiency is going down, and also temperatures in general of the systems go down. You can see individual cooling heat sources are going down. The least one is the oil cycle, so this stays rather constant here. The heat rejection stays rather constant, versus the largest drop in heat rejection is here on the high temperature turbocharger intercooler. The solution to the riddle is simply that in this case here, it's not the engine that produces this increase in fuel efficiency, is actually the cooling tower that is throttled, because at a certain load level, the heat becomes the bottleneck. The heat produced by the engine becomes the bottleneck for the chiller. The chiller is being throttled as well, and the cooling tower is reducing, is starting a recycle flow, and it's reducing heavily on its own aux load. That is shown in this small graph down here. And this actually, an overall fuel efficiency is going up because the auxiliary load of the plant is actually reduced much more than the actual decline in engine efficiency. Second example, now exceeding 90% very clearly, more than 97% fuel efficiency in this cogeneration plant, the district heat plant, that's actually similar to a plant that's actually been built in northern Germany. This example here is a Jenbacher 920 B8101 gas engine, the 60 Hertz version of the 920 engine that's used in this Stapelfeld plant in Germany, which uses a trick, or two tricks actually, to come to this efficiency. By simply heat extractions, you will end up here with a range of 93% as the maximum you can get if you look at reasonable exhaust temperatures from the stack. But there is two units here. One is a compression chiller that actually uses heat, produces heat from a cold water source from 96F to 82F to produce 140F. That is also used here in this district heat cycle. And the source of this cold water heat is coming here from a wet heat exchanger. A wet heat exchanger does not only cool down the exhaust to, cools down the exhaust below the dew point of the water contained in the gas. And this allows for gaining here an extra megawatt, almost an extra megawatt from the exhaust gas. So the exhaust temperature from the plant running this wet heat exchanger is about 110 F. So in a load study of this plant, here is the load fraction from 0.4 to 1 of the gas engine without the wet heat exchanger and compression heat pump. You are in the range that you would expect for such cogen plant, 92 to 93% fuel efficiency. With the wet heat exchanger, you come to 97% at the cost of the, because there is so much flow in the hot water, last sentence, the target temperature target of 220 F in this plant cannot be reached, and you have to actually bypass the wet heat exchanger at the cold end to allow the temperature of the hot water supply to go up again. Something I have to show to anybody who's interested on the model directly. Doesn't come up here with enough detail. To sum up, I've presented an engine model that includes the control schemes for temperature and flow of the cooling cycle of the engine, and that allows to look at performance of an entire CHP plant with more detail, and in particular with regards to off-design and part load operation. The limiting factor may, on the one hand, be this control strategy of the engine, so certain temperatures that are required. On the other hand, it may be with the cooling cycle of the cooling equipment or other equipment in the plant that limit the performance of the overall system. Finally, I have as my belief and my conviction is that accurate simulation of a power project brings much value to the investment decision or any modification decisions if you look at the entire operating range, because fluctual operation of design will be the more likely operation in every unit in the power generation in the future. With that, I want to close my presentation. Thank you very much for your attention.
Thank you, Joseph. All right, our last speaker. All right. Thanks for staying, everyone. Our last speaker is Roland Keiss, who is Sales Director responsible for North America at MAN Diesel and Turbo. Mr. Keiss is situated in Houston. He joined MAN Diesel and Turbo in 2009 as a mechanical engineer and carried out several roles within the organization. He studied mechanical engineering at the Universities of Kempten and Augsburg, Germany, as well as the University of Newcastle, Australia. With that,
thanks, Peter. I will try to speed up so we have some questions at the end of the session, and of course you won't miss your lunch. I have structured my presentation into looking a little bit more into the energy market demands, looking worldwide and also especially and the demands for the US. Out of this, we clearly believe that there's a huge demand in future scenarios for larger scale engines and CHP applications. I will show you how we approaching these markets, and I will present two selected references that we have recently built in Germany. On this slide, I want to present where we see the development globally and also in the US market. So recently we are coming from central large baseload generation power plants where we have power generation only on demand. The focus was on electricity production. It was a stable and predictable market with power plants operating on baseload operation. Saying this as a future scenario, I would even say that we are there already, but it might be getting more extreme due to recent developments on the renewable side. So what we see, we are looking into decentralized, localized generation concepts. We see a lot of surplus, for example, looking into California. So there are huge solar fields. So they have production during lunchtime. So they need to store this energy or sell it somewhere else. Of course, CHP applications with high efficiencies. We are looking into 95% of overall efficiencies. And then going from the stable market to a volatile and flexible market. So with huge demand on flexible power, which needs to be at the grid within 5 to 10 minutes. Saying that, also the operating hours going down, so we see a tendency to lower operating hours to back up the renewables. These 4 pictures can show you what I just told you a little bit more visually. So you can see a baseload generation. So you can see this is a daily curve. So of course on lunchtime there's a peak demand. In the past there was baseload. There still might be in case we have wind generation which can cover the peaks. Then you have solar tying into this. And this future, or maybe we have it already, this scenario shows you that there's a certain surplus generation. And of course there also battery systems will tie into this. But you see in this scenario that there's no baseload at all. So here we see a huge market for larger scale CHP applications. Speaking about renewables, just to give you an idea who is leading the renewable sector, so it's China for now, but United States just behind, and then Germany is on 3rd place. And And what we clearly see here on this picture, on the US market. So looking into the year 2040, the renewables are supposedly to double. And that, in our opinion, gives a chance for CHP power plants to back up those gaps that renewables create. Well, this slide might be a bit confusing on the first glance. What I want to point out here is basically, so from the various sources of prime electricity, in the end, you use 40% for electricity production, and there's a rough number of 60%, which is wasted in the US. So there's really potential to do more on CHP applications. Certainly this is driven by prices, and we talked about this today, looking into electricity prices, and we are also looking especially into gas prices. We saw in the past it's hovering from 10 down to 3. So the predictability is, it can only give an indication, but even from a low price scenario to a high price scenario, the message is that it's gonna be, the gas price is gonna rise. And since we compare this to Europe, so we have a gas price of $8 for MMBTU, we see these larger scale CHP power plants built. And we expect the same also in the States and globally. So this is our solution for a 20 megawatt total output engine generation plant. So you can see the engine down here, then you see the auxiliary systems, which are located right here. You see the SCR catalyzation system and the boilers here, and the radiators basically on the roof. The building is concrete, so it can be prefabricated, and it's fast on the commissioning side. The total efficiency goes up to 95% for this model, always depending on the temperature levels which the customer can extract in heat. With this slide, I want to show you how we can produce, like, this is a 20 megawatt slice, and you can easily double it, triple it, and so on. So the benefit is it's prefabricated, it's ready designed, and it can be adapted to certain temperature levels that different clients might have. We've seen this slide before. It's a little bit more simplified. So basically where we can extract heat is from the exhaust gas, from the cooling water, and if possible from the loop oil circuit. So that gives us a chance to extract heat up to efficiency of 95%. So we can either extract hot water or steam on top of the electrical efficiency. That's an example, basically the very same engine, but with a chilled water circuit. So you can extract hot water and cold water. So with this slide, sometimes I get into trouble with my colleagues because we also produce gas turbines in-house. But this is certainly a huge advantage of the recips. So the fast startup times to full load within 5 minutes. The many starts you can do without increasing maintenance intervals. You can go to a part load down to 15%. And there's a stable load profile at high temperature levels. This slide illustrates a 40 megawatt power plant comparing recips versus gas turbine combined cycle. So you can see the efficiency. So if you have only one gas turbine, of course, once you go down on the load, the efficiency goes down tremendously. Having 4 engines, you can balance them. So once you need only 20 megawatt or 30 megawatt, you can shut down one engine, you can have those in part load operation, and the efficiency will be hovering around 45 and 50%. So this is basically the portfolio on the gas side. So we have a 10 megawatt unit, which is single stage turbocharged. So the efficiency, depending on the various setting that we have for this engine, goes up to 48.8%. Then there's a 2-stage, that means the TS, 2-stage turbocharged engine of this version, which has a electrical efficiency above 50%. And both have an efficiency in CHP applications up to 95%. And then we also use the 20 megawatt unit, which has an electrical efficiency of 49.5%. The total efficiency in CHP application goes up to 90% because the lube oil temperature levels are a little bit lower than for the other 2 engines. So I selected 2 references on CHP because we saw these developments in Germany and in Europe. So gas prices are higher than here, electricity prices are higher than here. So these power plants are built right now. So this one was already built. It's a 120V 3544G gas engine. Electrical output is 10 megawatt plus approximately another 10 megawatt on thermal output on hot water production. So this was like a brownfield application. So this is not the slices I've shown you before, but we managed to fit the engine and the whole system into an existing building. The result is we could reduce the CO2 emissions by 40%. The second example that I have is also in Germany. It's in Stuttgart. So this is a coal replacement power plant. It's 3 units. So in total, it's 60 megawatt on output. It's a little difficult to read, but the CO2 reduction is 30%. Then you have the NOx reduction. You have particle reduction up to 0. So compared to a coal power plant. And we see this more and more coming, that coal and nuclear is going to retire in Europe, especially in Germany. And these power plants will certainly have to back up the increasing number of renewables that we see growing. Well, thanks for being here, and I think we have time for questions right now. Thank you.
Thank you, Roland. All right, so I'm going to ask our presenters to stand up here at the podium and field some questions. We have about 20, 25 minutes for questions.
Just real quick, from your presentations, thank you all. I thought they were all excellent. And actually, I kind of had a combined heat power station. But maybe you can just, at a really high level, what's driving, more combined heat power stations? Is it the renewables, or is it the efficiency that they're getting, or is it kind of a combination of those sorts of things?
Well, I would say it's a combination. It's certainly that renewables are coming more and more, creating gaps where there's no renewables available. Plus, also the electricity prices, gas prices that are increasing. So which is driving the new build power plants into higher efficiency demands.
Just real quick follow-up. So the renewables, so all these combined heat and power stations continue to be connected to the grid so they can kind of import power in or make their own power? Is that usually the configuration, or they stand alone?
Well, that's what we are more looking into on the larger scale, but I think the smaller units, they can be also like in microgrids. I mean, we are also looking into microgrids. It can be standalone, but it can be tied into a local.
I think to add on to that, I think you're seeing companies are smarter in how they buy their energy. And they see, you know, nobody comes to any of us, any consulting engineer and says they want to put 3 engines in the back of their plant. They come to the engineer or consultant and say, I have a pinch point. I'm either spending too much on my thermal or spending too much on my electricity. Find a solution for me. And usually those are going to be grid-connected solutions. And most of the time in the combined heat power applications that we see, it's behind the meter. They're very rarely exporting onto the grid. They're trying to offset anything that they're purchasing. But the main driver we see is just people are smarter on how they purchase their power.
And to kind of follow on that, if one of the options we looked at was a gas turbine option. If we tried solely going gas turbine without doing any duct firing, we would have needed to install somewhere in the neighborhood of a 50 megawatt gas turbine. So we would have been exporting just to make the economics of the project work. So it really is economics driven and what your needs for the heat is and how desperate you can have it, whether it can be interrupted or not. That changes a lot of it.
Thank you. And finally, as a commercial factor, the quick startup is a lot of money because you can go in secondary research markets, and that's a good market, at least in Europe. Sure.
Yeah, I mean, and further, I'll just jump in. I think we're going to see an increase in CHP applications between now and in the future for a whole host of reasons. One is renewables. The influx of renewables is creating some uncertainty and lack of dependability on the grid and costs, okay? And so I think industrial applications, we're going to start seeing an increase in CHP applications for those reasons, to try and save some money because gas is so cheap here in the U.S. as opposed to Germany or in Asia, for example. But that's my 2 cents on it. I don't know if you have anything else.
Some things have to change, though, in order for there to be that wholesale expansion and growth. So I would just ask the panel to comment from your perspective, what needs to change in order for us to see an increase in the deployment of CHP here in the U.S., number one, and then number two, how does that apply to what you're seeing globally?
Well, one of the things I would say that we're already experiencing is the change in the mindset of the utilities. 10 years ago, the C in CHP stood for cancer as far as the utility was concerned.
Cancel.
Yeah, and so, the fact that they're now offering incentives to try and help solve some of their problems. And there is a fundamental shift in it is a lot of the utilities are now looking at these kind of CHP facilities in a more of a partnering approach. And what can you provide to the utility as a whole, which just didn't exist before. It's like, no, I don't want to even hear what you're doing. So that, I think the change is already starting for good.
I think the example of that was one that Rick highlighted on in Brooklyn, was it? I believe with the offset transmission and distribution upgrades that were pretty significant costs. So that was an easy sell to the utility to do that.
Yeah, that was a Brooklyn Queens demand management program, and I do think that the shift in the attitudes from utilities is definitely a big change, and more of that needs to occur. And I had mentioned earlier, but we have some of these grid mod efforts, the REP program in New York and others, and that's really is making a difference in how utilities look at combined heat and power.
And the interconnections. Everybody talked about the changing utilities. Years ago, 2001, 2002, when we were looking to do what Chukru was doing in Alaska, we were doing that for Wazoo and Pullman, Washington State University. They had a coal plant. We were going to convert it as Trigen Suez, convert it to gas turbines. Well, we went to go close the deal, and the utility tripled the price of the interconnection at the last minute, and we got up and walked out. I mean, now they want to partner with you because they're shutting down coal plants. They're not going to build another one. They're not going to build, you shut down a 500 plus megawatt coal plant. You're not putting in a 500 megawatt combined cycle plant, right? You're putting in peaking, you're putting in something smaller. Well, now they're welcoming, the CHP and, what you can provide for them over the fence if that's a viable opportunity for you.
You're seeing that, and one of the great example of that where the coal plants getting shuttered is Upper Peninsula in Michigan.
Yep.
They're doing a lot of on-site generation at some of the large industrial customers up there, and they're being used to support the grid.
So how many of you feel that utility as a service or a developer build own operate model and partner with the utilities is going to be a major contributor in the future?
Well, I think it's going to be a major contributor. You're seeing more and more utilities open up groups that their only job is to find distributed generation projects to own and operate. You know, AEP in Ohio has a whole group that they just search for high-end industrial users in their AOR that they can help save money.
What are some of the barriers that you see that need to be fixed immediately to see a more rapid deployment? Is there anything that you could point to, one or two things that you think that we need to collectively as an industry be working on or focusing on?
Well, one of the ones that I always get a kick out of is, you know, an area to improve that is when you start looking at a renewable project. People get excited about a renewable project and because of the less environmental impact that occurs by doing it. Well, when you start looking at these CHP projects, you're looking at, you know, double-digit efficiency improvements, and a lot of people are just kind of like, yeah, but it's not a solar panel. and that sort of thing needs to be pushed forward, both on the regulatory side as far as the environmental thing, but also as far as the utility interactions.
Try permitting a reciprocating engine on a biogas project in California.
You're talking about renewables, and have any of you installed a renewable CHP system using the new fuel cells that take water, break that into a hydrogen plasma, and then burn that hydrogen plasma in the CHP system?
I can actually answer that one. Our university has been studying fuel cells. We've actually put a few of them in operation. And our leading fuel cell guy had a very interesting quote about that. He says, fuel cells an emerging technology. They've been emerging since the 50s. They just haven't come out there. We're currently in negotiations with DOE to potentially do about a 10 megawatt site fuel cell being located on our campus. Again, it's just something that's not quite there yet.
So the hydrogen for that project you're going to get from coal?
Yes. Yeah, it was actually, the project is actually, is even funner than that. It is a coal gasifier to provide a syngas fuel source for a recip engine to regulate wind. So it is coal enabling renewables, is the one interesting tagline. And as an adder to that project, they're looking to take some of that gas off and run it into a fuel cell.
What size engine?
I think
Hold on, I can help you.
I think that's one of the things that we don't often talk about is the true cost of integration and firming support that renewables require. So we've been so excited to use the Greenspan term, a lot of irrational exuberance and just wholesale licensing and issuing of renewables, photovoltaic and wind, and yet the utilities are getting killed on their operations. They're stressing their assets more than ever before in the history. They're having a harder time making their margins work. Utilities back is being pressurized by the renewable, the spread of renewables all across the U.S. And so until we also begin to face the facts, which that's one of the things I really appreciate about your coal project, is that you're coming at it from a very practical standpoint. We are honestly looking at our options, and we don't have a ton fuel-wise. So we have to consider something that is not popular, and yet it still turned out to be the most economic, the most efficient, and in your analysis, the cleanest solution that you can come up with to solve the problem. And so I think we need more of that practicality.
I just got a quick for Joseph.
contributing. The developer is a German company. But,
Yeah. Because we just started putting a model together, and we are using that model. It seemed to be the best model to use for a CHP plan.
Thank you.
I'll put a plug, but
Yeah. If you want to see or you want to discuss,
yeah, I might want to do that with you.
come by booth 6543. Sorry, Peter. I can demonstrate them all.
Just one note, I mean, we've all been probably to some renewable or there's the irrational exuberance about it, but I know there were some case studies in Alaska and remote locations in the Aleutians where they actually were successful at high percentage penetration of renewables, a combination of wind, solar, in very small villages and some innovative management, which doesn't really expand to large utilities. But I think, with storage starting to come on, that, in a 30 or 40-year horizon, that high penetration renewables will probably be coming in. I don't think it's a permanent situation where we're going to see the large gaps. It's in the future to get a higher penetration of renewables without gaps.
Any other questions or comments?
Just curious what your thoughts are about the integration of batteries with CHP. And if you think maybe that application with the CHP is something more beneficial for like a microgrid, which goes to your college.
Yeah, I can actually answer that. Our local grid, looking to make sure I don't have nobody from my utilities here. Our local utility has a 50 megawatt UPS grid connected for solving a problem of not having enough spinning reserve on that end of the system. So they have this asset in their system, and they are not even using that to regulate wind. They're using their LM6000 gas turbine to the cost of about 14 million gallons of extra fuel a year because they're having to back it off on the efficiency curve. So you kind of put that in perspective, it's a 30 megawatt wind farm, and they're not even using their own battery because it's too expensive to operate. The gas turbine is cheaper at the 14 million gallons of fuel oil a year. So it's an almost thing. I have talked to a couple of battery people. There's a potential if you have a battery bank big enough, that if you just kind of cycle it on the very, small, don't deep cycle, but just kind of use the battery kind of more as a capacitor, it can do that forever without degradation. But the problem is you need a huge battery so you can operate in that range, and then it becomes no longer cost effective.
But it's certainly a future scenario.
Yes.
What we are looking into. So
Absolutely.
battery systems will be coming. They will be backing up either gas turbines, engines, or renewables. I'm certain about this.
Most of the talks or most of the looks that we've taken today have been talking about an individual plan or a singular application. One person, don't remember who, made the comment about aggregation and aggregating together a large number of distributed assets into an entire grid support network. Any comments from the group?
Well, just as an example, that is possible in Germany. In Germany, you can sell as a conglomerate of small units, you can sell into the grid. So it's a commercial.
The largest number, I think, Rick, you put in your presentation was in the small size ranges, the 500 kW size units, largest quantity, and they get smaller the larger you get. There are several examples in some countries, Iceland and Germany, of small distributed projects at 500 kW, but literally 20, 30, 50, 100 projects being aggregated together and then packaged as a portfolio. I think that's one of the things that is one of the potentials we see, and in this partnering with the utility and looking at coming up with a utility as a service, this can start to make some real sense with the technologies that we've been talking about today.
Well, you're seeing more and more of that. Once again, there's companies out there, especially in PJM, that will acquire generation assets, whether they're existing standby generator sets, diesel, natural gas, retrofit them with the emissions controls, and then sell that capacity into the grid. You know, there's a large market, and you're seeing more and more applications for that, especially customers that, you know, have an asset that's a standby generator set that really they can't get any they can't monetize. And by maybe putting retrofitting some emission controls on it, they can monetize that asset and have somebody else control it, sell it into the grid, but still get some of the benefit. But you're seeing more and more of that.
This might be an observation, I don't know, but I mean, I listened to the keynote speakers yesterday, right, and they kind of went off some trends, right? One was the combined cycle efficiency, we're going to 65%. I think someone from Mitsubishi might have mentioned that, right? And somebody on the wind stuff. I got to tell you that this presentation was a little bit of an eye-opener for me, right, in the sense that I actually didn't know you could attain 95% efficiency with a CHP plant, right? And I think maybe next year they ought to have at least somebody on that keynote speaker panel that kind of demonstrates that because there were a lot of projects. I mean, I was also impressed with the number of projects that the panel kind of put up there that were out there, at least on the books, that are possible to be CHP projects, right? So that's just that overall comment that came up. I thought.
I'll follow on with that. My 50-plus-year-old plant is in the high 60s. So.
Appreciate your comments, thank you.
Can I add on to that? I'm new to this segment, so this is all educational for me. So, you know, to his point, and seeing the high efficiencies of the recent plants, what is the advantage of having combined cycle? Why is it such seems like a main part of this category? And I mean, I know the recent engines are making progress, but why aren't people catching on to that faster?
Well, it's really dependent on application.
Yeah.
You know, size and application. You know, if you look at a refinery in Houston, Texas, they need the amount of steam and thermal BTUs that they need far outweigh any value of electricity that we can sell. So they're automatically going to be driven towards the proper solution of a turbine of some size or shape. You know, recips have a space, 5 megawatts and below. You know, I mean, ideally, and hot water. We're really good at making hot water. Not so good at maybe high. Not good at high-speed recips. Medium-speed recips, we go up to 10 megawatts, no problem. We got some really. We both have really good lines of engines for that. But it's really applying the equipment properly to the application, and that's the key. And that's where the tool like this can come into account. You know, but steam, you know, turbines really good at making BTUs, and engines are really good at making electricity, and that's the simple.
In industrial applications, typically the gas turbine, if you need high pressure steam, high temperature steam, the gas turbine has much higher exhaust and much more exhaust. That is helpful. But when you look at the applications we saw here, beverage industry, pharmaceutical industry, engines make absolute sense. And district heat, for sure, because you're in the right temperature.
It really depends on your balance of how much heat you need versus how much electricity you need. And that's really what drives your selection of your combustion source.
Yeah, so we do this all the time for various universities. One project, Arizona State, they were power forward. They had a lot of chilling for some reason, and so that application we used a gas turbine. We took a bit of the heat off of the back end and used it for the campus steam system, which had humidification and sterilization at their research labs and things like that. Completely different situation in Fairbanks. For some reason, they're really concerned about heat. I don't know why. And so they would be what I call a heat-forward plant, where the primary product out of the CHP needs to be steam. When you do that, I tend to go away from gas turbines because the gas turbines make power, and you get a little steam out of the back. Boilers make steam that you get a little power out of. And so in a situation like UAF or anything in the northern states, I would go straight for a boiler to cover the heat first, and then make whatever power I could out of the CHP cycle. It's all, what do they need first?
Yeah. That's what we always ask every customer. What is your pinch point, and then we go from there.
Any other questions? I'd like to thank our panel.